So we looked at some techniques for doing this kind of averaging. One is the summation technique, which explicitly adds up the cost of all the n operations. The second one was called the charging method, and the third one was called the potential method. The potential method has a bit more flexibility in terms of what kinds of situations that it can handle. So we used vectors and hash tables to illustrate how these amortized analysis can be used to reason about average costs when the data structure itself needs to be resized and the resize operation is expensive. Then how can you reason about the costs? Okay, so today we'll use amortized analysis on disjoint sets. Okay, a data structure that we looked at in the context of spanning tree algorithms. Okay, so the notion of disjoint set is that you have a set of elements, right? So say n elements, and they start off in a set of their own, and then there are two types of operations that you can perform. One is called union, the other one is called find. Okay, so union operation takes two existing sets and makes a new set, and find basically finds out which set a particular element belongs to. Okay, now the key point here is disjoint set, so you cannot have the same element belonging to multiple sets. Okay, so the data structure is can only handle situations where sets are all disjoint. Okay, so they are represented at some level as an inverted tree. So this says that B belongs to the set E, or E and B belong to the same set. Okay, so by and large you can say that who is the child and who is the parent doesn't really matter, because it's a set, and so there's in a sense no ordering on the elements of the set. So when you keep them in the same tree, that means they're all part of the same set. Okay, to find out if two elements belong to the same set, you simply follow back to the root. So for instance, G and A, you follow to the root of this tree from A and from G, and if you reach the same root, that means they are in the same set. If they are not in the same, they don't reach the same root, then they are in different sets. Okay, so now you have these two operations. Make set creates a set initially, right? So the set initially just consists of the element itself. So pi stands for parent pointer, right? So pi parent. So you set the parent to itself. That's a way of representing a set that contains only one element. Okay, so and then you may maintain something called rank. We'll come back to this. Why you maintain the rank later on. So find simply follows the parent pointer, right? So while x not equal to parent of x, then you set, you set x to be the parent, and then you keep doing that until you reach the root, right? Because at the root you have set phi of x equal to x, and therefore you recognize the root by the fact that the parent of the root is itself. Okay, and when you reach that root, you just return that. That is the, and then you have this union procedure. So if you want to union two sets x and y, you realize that when you try to union, you may not, in this example, right? You might say union B and G. Okay, so what you need to do is you need to find essentially the root of the set containing B and the root of the set containing G, and then make a pointer from one root to the other. Okay, and this is captured here, right? So you have you find the root of x, you find the root of y, right? So you are given two sets union x and y. You find their roots, and then you set one to be the parent of the other, right? So now you can see that the sets, so when you started out, right, the set containing X was an inverted tree, the set containing Y was an inverted tree. Now you put an edge between them, therefore everybody is connected, so they're all part of the same set. So you can see that union is very efficient, right? It takes O of 1 time to do union, whereas if you thought about, you know, a more obvious set representation, unions take linear time, right? So you have to essentially, let's say you keep a set using represent a set using a sorted array. Okay, so then when you need to do a union, you need to merge these two arrays, and then that takes linear amount of time, right? So, and in addition, you know, that representation of set, the normal representation of set is not meant to support a query where you try to find out which element, what set an element belongs to, because that notion of give me the set that this element belongs to makes sense only in the context of a disjoint set, right? Otherwise, the same element may be in a million sets, so you don't really want to return all the sets in which an element is present. So the find operation is really meaningful only in the context of a disjoint set, and that's where this data structure comes in. So, so it's clear that find, because you have to chase the pointer path all the way to the root, find is going to take time proportional to the length of the path from root to leaf, right? Now union takes O of 1 time if you ignore the find, okay? And you can sort of, from here on, you'll just ignore find that are included in union, because you can think of, you can limit union always to be performed on the root nodes by simply adding 2 more finds in front of them, right? So essentially, let's say you have n unions and finds, then you can convert that into at most 3n unions and finds, such that all the unions are on roots, right? Because what you do is you replace the original union that was like this, which had 2 finds and a single pointer updating operation, into 3 operations, 2 explicit finds, okay, and then you only do a union on the roots. Okay, so this way you ensure that union will always take constant time. So now the interesting question is whether you can construct from this example a case where where a set of n operations will take O of n squared time. Can you think of how you can issue, again, this is the initialization step, right? Every element is put in its own set. Okay, so assume that that is the initial state. Now you have to find a sequence of order of n operations, okay, finds and unions, such that at the end you would have spent O of n squared time. Okay, so clearly, if, let's say you keep doing finds and never do a union, well, every element is in a set by itself, therefore all finds take only constant time, so that's not going to be the example, right? If you keep doing unions and never finds, well, of course, once again, because unions always take O of 1 time, so there's no cost there. So obviously you have to find a combination of unions and finds in some order, and then you may be able to create a workload where O of n operations take O of n squared time. Can you think of how to do that?
If we always add the element to a leaf node, then the new element becomes the root. Then every time you do a find to do the union, you go all the way up and then add 1, and then the tree gets longer and longer, so it's 1 plus 2 plus 3 to n.
Right. Or you can also do something, you can construct even a simpler example where you essentially do unions that constructs a chain of length n,
yeah,
right? And then keep asking, doing a find on the leaf element, right? that's also a valid example. So it's just, of course, it somehow doesn't, it seems less interesting than the one that you mentioned, where you're asking for find of different elements, and still it'll be O of n squared.
No, what I was saying was making this chain, like you said, but to make it you have to do the find for leaf node every time. So
no, you just have to say, okay, union.
Oh, okay.
Right? So initially they're all like this, right? Right? So you can say union n with n minus 1, n minus 1 with n minus 2, all the way, right? So basically unions proceed that way. So essentially that means you're going to end up constructing a chain from right to left, right? Now if you ask find n, that's going to take O of n time, right? Okay, so this is obviously something that we don't like, because we thought this is an efficient data structure, and now we are finding that we take O of n time per operation, which is not good, right? So let's see how can we improve this? Okay, so one way of doing this, right? So again, we can see that the problem is created by this chain, or the fact that we are creating these unbalanced trees, right? So the question is whether we can somehow create more of a balanced tree, because if it's a balanced tree, then the depth cannot be O of n, right? The depth has to be more like log n if we can make it balanced. Okay, so how do we make it balanced? Well, it's actually quite simple, right? So you can keep track of essentially the depth of a set, and then whenever you have to do a union, you can point the set with lower depth so that it points to a set with higher depth. Okay? So the depth is represented by rank, so you can see how we update the rank in the previous example. Well, I guess we don't show here how the rank is updated, it just shows the initialization of the rank. Okay? So now in this algorithm, this modification, you're going to not only initialize rank to be 0, but then you're going to update the rank. Okay? The rank is you can think of it as the depth of the tree, okay, or height of the tree. So when you are going to do a union, what you're going to do is you're going to take consider the heights of the two trees. Then you're going to take the shallower tree, which is Ry in this case, and you're going to make the shallower tree as the child of the deeper tree. Okay, so this makes sure that things will stay balanced. Okay, or in particular, okay. So in addition, what you need to do is you need to keep track of the depths, right? So if R of x and R of y are same, right? If the depths are same, then when you make one of them as the child of the other, then you are going to increase the depth, right? Because let's say, let's consider this set, right? So the depth here is 2, right? So if we have another set whose depth is 2, then if you make this the parent, now the depth of this is now going to be 1 plus the depth of this, right? Because you're putting one other pointer, right? So the maximum depth is going to increase by 1. So if they have the same heights, then when you put a parent pointer from one of them to the other, the height increases by 1. But if they are not the same, then you're simply going to make the smaller tree point to the larger tree, in which case the larger tree's depth is not going to be changed because the larger tree already has subtrees of the same rank, right? So that's the so the example. So if you have two trees like this, then you know that because the depth of this is less than the depth of this, you're going to make a parent pointer this way, okay? And because this chain has a longer length than this one, the addition of this arrow is not going to increase the longest chain below this, right? So as a result, your rank is not going to be updated in that case. The only case where you need to update the rank is if you're merging two trees, both of which have the same rank. Okay? So now, I claim that the tree, now what do you think is the cost of the, what is going to be the amortized cost now with this modification? We have n operations, how long do you think it's going to take? So, again, it is the find that costs, right? Union is always cheap. So it's a find that costs. And the cost of a find on a set is equal to the rank of the set, right? Or rather, rank of the root of the set, right? Because we're just following the pointers all the way to the root. So the height of that tree is going to tell you how much it costs to do a find on that tree, right? So now that we know that the cost of a find is given by by the rank of the tree, can we make an argument as to how can we use that information to reason about the cost of n operations? So the key point here is that each time the rank increases, right, then the number of elements has to at least double, right, in that set, because we are doing only case where the rank is increased is if the rank of the two sets are the same, right? That means they are of the same size, and so when you increase the rank by 1, that means now you have something that has double the elements. Okay? So you can say this is a very commonly applied analysis technique that you are doing an operation and you can make a reasoning about the operation that says that each time some quantity increases, it is in a collection that is twice as long as large as before. Okay, so with that reasoning, then you can say that it takes. So from that, you can go ahead and show that in fact the height of a set is going to be log r if r elements are present, right? If the size of the set is r, then the rank of that tree would be log r, right? So that's what you'll be able to prove, and from that. You can come to this conclusion. So let's try to understand this a little bit better. So that's the initial case. You have all the make sets, okay? And now the superscripts here denote the rank. Okay, so originally all the ranks are 0. Then let's say you do these 3 unions, union AD, BE, and CF, and because they have the same rank of 0, it doesn't matter which one we make the parent of the other, right? So we make A point to D, B point to E, and C point to F, and now the rank of these have increased, right? It's no longer 0, it's become 1. Now we do 2 more unions. We union C and G and E and A. Okay, so if you recall from the previous picture, right? E was already in a set with 2 elements, right? And A is also in a set with 2 elements, right? At the bottom of the slide. So when you union them, you're going to get a set like this with 4 elements. And once again, these two have the same size, so you should make one of them point to the other and increment the rank of that bigger one, right? So now, again, what it shows you is that the length of the path now becomes 2. The other one is union of union of C, comma G, where I guess G was already in a set with 2 elements, and C was already in a 2-element set, and G was in a set by itself. And in this case, because G has a rank of 0, right? And C is an element of a set which has a rank of 1, so you have to make G point to F. Okay? And in this case, because the ranks of the 2 sets being unioned are not different, the root rank does not increase. Okay? And then at the very last step, we do a union of B and G. Okay? So now you can see that B and G, so this set has a rank of 2, this set has a rank of F, so you have to make F point to D, and again in this case the rank of the root does not change. Okay. So this sort of gives you an idea that somehow it gives you a flavor of how the tree tends to get wide rather than deep. Okay, so let's do a more careful analysis of disjoint sets, right? So once the asymptotic complexity of mixed set is unchanged, and union has become a tiny bit more expensive in the sense that you are checking in the rank and so on. It's only adds only a constant amount to the cost of union. Doesn't really change its cost in asymptotic sense. So now what about find? Okay, so a sequence of n operations can create n more n elements. Therefore, the number of finds, the maximum set size is order of n. Okay, and with union by rank, each increase in rank can occur only of a doubling of the elements in the set. Okay, so as you go from rank 0 to 1, you must have double the elements as a set with rank 0. As you go from 1 to 2, again you should have double that and so on. So easily you can see that in a set of size n, right? So the number of so what that tells you is that if you have a set of size So what this tells you is that it is making. So the point here is that if you have a set of size k, right, then it's going to have at least 2 to the power k elements, right? Because that's what you get from this observation, right? So each time the rank increases by 1, you have double the number of elements. Therefore, by the time the rank gets to k, you should have at most 2 to the power k. You should have at least 2 to the power k elements in that set. Okay? The total number of elements being n, that means, we are just saying that the number of sets of size k, right? That's the number of, I'm sorry, it's not size. Okay, so let's just talk about size L. Set of size L must have, log L or the other way of saying this is that set of rank k must have 2 power k elements or more, right? So since there are only n elements in the whole set, that means the number of sets with a rank k, right, have to be no more than n by 2 to the power k, right? Because each set, for a set to have rank k, that set should have 2 to the power k elements. So if you have only n elements, then you can have only n by 2 to the power k sets of this size, and therefore the number of nodes with rank k can be only of the order of n by 2 to the power k. Okay? So in the worst case, right, so k is going to be, or a very, the corollary of this is that the height of the tree is no more than log n, because you have only n elements, so even if everything is put into one big tree, right, and even then, the height of the tree is going to be log n, right? So that's one technique for essentially making your unions more efficient by keeping track of the heights of different sets and preventing, preventing the degenerate cases where you build long chains. Okay, so now you build something that's more balanced, and that way you are able to ensure that it only takes at most log n time to do the find. So if you have O of n operations, then how long does it take? It takes at most O of n log n, because your finds have now been brought down from O of n to O of log n. Okay, so this is one way to do this. Here is a second approach. Yeah?
But this is not amortized analysis, right? This is just like worst case analysis, right?
This is amortized analysis because we are really talking about okay, so what you're trying to say is that even if we didn't you're right. So what we did was we considered the cost of n operations, right? N union find operations, and what we showed was that that can cost O of n square, right? And then we said, okay, here is how you can change the algorithm so that you get a lower cost. Okay? So what we are working towards is a way to do a more tight analysis, but we are going to get there in steps, right? So this is one step, and so you are right, because in this case, all we are saying is the worst case for any individual operating is log n, therefore the worst case for the n operating is n log n, and we aren't being really clever about that in any way, right? So, we had what we did was we had fast unions and slow finds, right? So here is a dual data structure that gives you fast finds and slow unions. Okay, so that is called a threaded tree, where what you do is it's still an inverted tree type of data structure, but you make sure that every child is at level 1, right? So whenever you have to do a find, you have only one parent to follow. Okay? Now, if you want to do a union now, you have to flatten, right? But if only you had only these back pointers, then there is no way for you to get to Q and R from P, right? If only you had up pointers. So in order to reach all the elements, you keep them as a threaded tree where all the leaves are kept in a linked list. Okay, so you have the root connecting to the leftmost leaf, and then you have a sequence of arrows so that you can, by following this chain from the root, you can reach all the elements of the set. Okay, so now it's obvious that find now is fast, but union is going to be slow, right? So why is union slow?
It should be fast, right? Because every node has the parent is the root, so we can just point to that root.
So you can point from D to Q, which is, well, I guess in this case we have pointed from R to B, right?
Yes, you just make the parent of P is A. Oh, okay, you have to change all the parents.
Exactly, right? So sometimes when you see the picture, you may miss some parts, right? So there are two things that are going on when you do the union. One is this, these two threads have to be linked, right? So you need to take R and make it point to B. This is actually not difficult, right? Because given only the pointers here, this is somewhat expensive, but let's say you not only keep a pointer to the first element but also the last element, then you can in constant time update R to point to B, R to point to B, and then seems simple. But the real problem is that now P will no longer be the root. Okay, so now you've made A the root. Therefore, every child of P, its parent pointer needs to be updated, right? So there's no way around this, right? So there are a large number of parent updates that need to be done, and this makes it very expensive, right? So can we try something very similar to last time so in this case, right, so we have constant time O of 1 find and linear time union, right? So can we reduce the cost of union so that it's no longer linear? So we can in fact apply a very similar idea. Again, keep track of the sizes of sets, right? And then make sure that it is the smaller set that is merged with a larger set. And the reason why this is relevant is, let's say in this case, if you make P a child of A, right? It is the parent pointers of Q and R that need to be updated, right? So if you take, whenever you're doing the union of two sets, if you take the smaller set and keep the root of the larger set as the root of the combined set, then what happens is that the number of updates you have to do is going to be proportional to the smaller set size rather than the larger set size. Okay, so that is going to make a difference. And let's see whether I have a detailed analysis here. So what you can do is so other than the cost of updating parent pointers, right, union takes only constant time because you just have to do this, linking of. So you can see that other than updating parent pointers, what we need to do is, right, in this case, P already has a pointer to Q. All you need to do is to have right, so all you need to do is to make A point to P, right, and then R point to B, right? So if you kept track of the last element in this list, right, which is easy to keep track of, then this whole thing, which involves basically getting to the last element, making it point to B, and then making A point to P, right? So those are basically 2 pointer updates. So those operations only take constant time. The only thing that takes more time is updating the parent pointers of Q, R, and P, right? So that is the cost that we need to account for, because that's the one that seems to be not constant per operation. So what we do is so we charge each element for the cost of updating its parent pointer. Okay? Now what we are going to do is we are going to count how many times a parent pointer needs to be changed. Okay? So what you can see is that each time you update a parent pointer, you're doing it on the smaller of the two sets. Okay? Which means that you can do the same analysis that they say that each time I update a parent pointer, the set is at least twice as large as it was before. Right? Because, so again, in this example, originally this set had, this element, for instance, was in a set of size 3, and after the change, it is in a set of size 7, right? So the size of the set has at least doubled, right? So what you can say is that each time I update the parent pointer of, let's say, Q, it's going to find itself in a set that is at least twice as large as before. Therefore, if I update it by log n, if I update the parent pointer log n times, by then that element should reside in a set of size n, right? And because size n is the maximum possible size of any set, the maximum I could charge to any element for updating its parent pointer is going to be log n. Okay? So once again, by keeping track of sizes and so on, using an idea very similar to the other approach, we are able to get a cost of average cost of log n per operation. Any questions? So in this case, we are using, in a sense, the charging method to keep track of the amortized cost, as opposed to just talking about the worst possible case. Okay. In the other case, we are still considering the net effect of n operations, right? So in the union by rank, we were still considering the net effect of all the n operations, and only then that allows you to basically say something about the cost being bounded by log n, right? So you do have to consider the net effect of those operations, but the analysis is somewhat simpler there, whereas here you do have to think a little bit more in terms of charting to get a simple argument about the cost. So as a very last step, we're going to talk about another improvement. Okay? So threaded trees do an eager union, right? That is, the union creates a data structure that's going to make subsequent operations fast. Okay, so in that sense, threaded trees are doing an eager union, whereas the original approach simply makes one link and doesn't care about the cost of subsequent operations. Okay, so that's something we call as a lazy approach, because you just make a connection and then you're going to later on figure out what is the implication of that connection between two sets. Okay? So the eager approach is better for find, but lazy is better for union, in the sense that lazy makes union fast, and eager approach makes find fast. Okay? So you could sort of think about switching it around and then say, can we do some extra work during finds, but stick to the same old, approach for union. That is, union, we just do a local update, one parent pointer, and we are done. But whenever we do a find, let's do some extra work. And that leads us to this very interesting idea called path compression. So the idea is very simple. Okay, so what we're going to do is that, suppose we are asked to find k. Okay? So what we have to do is we need to find the path to the root, right? In doing so, we have to compute all these parents, right? So once we compute these parents, why not at that point update each of their parents so that they go directly to the root? Right? This seems like a very sensible thing to do, because you are traversing the path anyway, you are getting to each of those nodes anyway, right? So why not just update their parents? And that's what is being done. So you do a k. So what happens here is that, okay, I'm sorry. So you do a find I. So what you're going to do initially is the parents of I are F, E, and A, right? So E is already, it can't be, it's already pointing to the root, so you cannot do anything better for E. But F can be promoted, right? And so can I be, right? So every vertex that we traverse along the path now becomes directly the child of the root, or is it the root itself? So I becomes the child of the root, F also becomes the child of the root. Now let's say you do a find k. Well, now what's going to happen is that again G is going to become a child of the root, and k is also become a child of the root, right? And you can see that after these two finds, the data structure has become very flat. Okay, and so it's an example of an idea where if I tell you the idea, it's obvious to you that this should work well, right? So because again, the whole idea is you are doing this work anyway, and just updating a few pointers along the way, so that later on your operations will become faster. Seems like the sensible thing to do. The question though is, can you actually show that this analysis, this improvement actually leads to a faster algorithm? Okay? So as it turns out, it really does. Okay? And what it does is it changes the algorithm from taking O of log n per operation to O of log star n per operation. And what is log star n? Log star n is, you keep applying log as many times to x as possible until you get a value of 1. Okay? And that's called log star x. Okay, how many other times you have to do log? That is called log star x. Okay? So log star of, right, so you can see that if I apply log 5 times, then I'll get 1, right? Because once when I do a log once, I'll get that.